Assalamu alaikum everybody. Welcome to our 11th lecture for the course Introduction to Artificial Intelligence. In this lecture, we shall look at the following topics. First, we take a little motivation about why neural networks were invented. What is the motivation? And then we look at the structure of biological neurons from which artificial intelligence networks are modeled. And then we look at the structure of artificial neural networks, which are normally called ANN for short. We look at the simplest of these ANNs, which is called single layer ANN or perceptron. We will look at how learning takes place in perceptron and what are its limitations. Okay, we're going to see that perceptron actually has a very serious limitation. Then we look at multi-layer ANNs. Again, we look at how learning takes place in multi-layer ANNs, usually through a process called backpropagation. We look at what are the design issues in multi-layer ANNs. And the final topic we shall study is deep neural networks, which we will look at briefly what it is about. So these are the topics we're going to cover, and they form our agenda for this lecture. First, the motivation. Well, what motivated the AI practitioners, the early AI practitioners, to think about neural networks is their observation of how human brain operates. As we all know, humans perform complex tasks like vision, recognition, motor control, like driving a car, natural language understanding. You can observe, for example, how a small baby at a very small age can understand his mother tongue and can easily communicate over a very little period of time. So how are humans able to do that? So the idea, therefore, is that if we can study how human brain works, then probably we'll be able to build machines that behave in a similar manner and therefore be able to perform such complex tasks, if not as efficient as the human brain, at least as close as possible to that. So this is the motivation. All right, so one way to build intelligent machines is to try to imitate the organizational principles of the human brain. So let us look briefly, therefore, at the organizational principle of the human brains by first looking at the structure of biological neurons. How are they actually structured? All right, now a human brain is a massively parallel information processing system containing billions of neurons. So it consists of a huge network of processing elements which are called neurons. A typical brain actually contains a network of about 100 billion neurons. That's 10 to the power 11. You can imagine how huge these neurons are within the brain. 100 billion. Now let us explore how each of these neurons is structured. This is the structure of a typical neuron. You can see that it has several components which are labeled in this diagram. We shall try to explain some of these. So a neuron consists of a number of components. The first and probably the most important one is the cell body. So this big area you are seeing is what is called the cell body, which contains the nucleus of the cell, and actually is the main processing power of the neuron, and therefore you can think of it as the processor. Assuming this is a small computer, then the cell body, or what is sometimes called the soma, is actually the main processing element. Now, branching out of the cell body are what are called dendrites. So these little fibers that you are seeing going out of the cell body, they are called dendrites. Now, dendrites are what are actually used to receive information or signals or impulses from other neurons. You can see, for example, here, this is a neuron which is connected to the dendrite of this current neuron, and this is actually used to receive information from that neuron. Now, one of these dendrites is actually very long, and it is called the axon. So axon is a single long fiber that branches out of the cell body, and it is actually the one that is used to transmit output to other neurons. Okay, so the dendrites are used to receive input, and the axon is used to transmit output. So you can think of it like our output device, therefore. And the last major component is called the synapse. Now, the synapse is the point of contact between the axon of one cell to the dendrite of the other. So in this case, for example, you can see the dendrite of our current neuron is connected to the axon of another neuron through the synapse. So synapse is the connection link. It is actually the one that regulates the information that is being received from the other neuron. Similarly, here at the end of the axon of this current neuron, there are synapses that will connect to the dendrites of other neurons. So the other neurons will therefore receive information from the current neuron through this axon, and so on. So this is how they are structured. So a neuron is connected to other neurons through about 10,000 synapses. So you can imagine the level of connectivity. This diagram is showing you just maybe about 3 of these connections, but actually there are about 10,000 of them for each neuron. So we have 100 billion neurons, and each one is connected to about 10,000 neurons. So you can imagine the level of connectivity and the information processing that is taking place within the human brain. A neuron receives input from other neurons, which are combined together. So this is showing you actually how the information is processed. The different input that is received from other neurons is combined together to form an amount of signals. Now, when this amount reaches a certain threshold, okay, so once the input exceeds a threshold, this combined input that is merged together from different neighboring neurons, when it exceeds a certain threshold, then the current neuron will fire, meaning it will discharge an electrical signal that travels down the axon to the neighboring neurons that are connected to this one. So this is basically how information is transmitted from one neuron to another. So you can see that the information has to be combined together, and this neuron will only fire when the neuron exceeds a certain threshold. So you can imagine, therefore, that biological neurons, in terms of their characteristics, they are massively interconnected. They operate in non-linear, parallel, robust, and fault-tolerant manner. Fault tolerance because these neurons, as the human aged out, many of them die, but you don't see any real weakness in the human because of loss of some of these neurons. Okay, so the brain continue to functions because of this large interconnectivity between them. Some of the neurons can die without the brain showing any effect in terms of its ability to learn and process information. There is the capability to adapt to surroundings. Humans are very good at adapting to the environment in which they are. Ability to learn and generalize from known examples. Okay, and the collective behavior is different from individual behavior. We just saw the way a single neuron works, but that doesn't explain how the whole system work to achieve intelligence. Okay, yeah. So the point is, can we, based on what we have just learned about biological neurons, develop an artificial neural network that has these properties? Okay, this is basically the objective, and to a large extent this has been achieved actually, as we shall see. So that's what I'm saying here. Artificial neural networks mimics some of the properties of the biological neural networks. So let us see the structure of artificial neural networks. An artificial neural network is designed to mimic the structure of a biological neural network, as you can see in this diagram. So on the left here we have the structure of an artificial neuron, and on the right we have a network of such neurons, which are organized into different groups which are called layers. Alright, so again we shall talk about this in a little bit more detail, but let's first of all look at the neuron itself. Say a neural net consists of a number of simple processing elements which are called neurons. Sometimes they are called units, cells, or simply nodes. Okay, so this is an example of an artificial neuron, or just a processing element, or just a node. Now each neuron is connected to other neurons by means of a directed communication link, each with associated weights. Alright, so as you can see here, these lines are input lines that are coming from other neurons, and each of them is coming with a certain input value. Okay, x1, x2, and so on. Now each of these input coming is multiplied by a certain weight. Okay, depending on the importance of that information to this cell, the information is multiplied by a certain weight. So this W0, W1, W2 are the weights. Alright, so in comparison with the biological neuron, you can imagine therefore these links are the dendrites, and the synapses are actually the weighing of these inputs by multiplying them with certain weights before they are later combined inside the cell body. Okay. Now, once each of these products of input and weights are received in the main cell, they are added together. Just like we said, the signals coming from other biological neurons to current neuron, they are combined together. So similarly here, these products are actually added together. Plus a certain bias is also added. We shall see the importance of bias later. And this overall sum is then passed through a function which is called activation function. So that activation function will produce a certain value which is then output to other neurons. So you can imagine, therefore, this output link is like the axon that we have in the biological neuron. Alright, so this is how a single neuron operates. We shall see a specific example of how these values are received, how they are computed in a moment. Okay, but you can see here now how they are combined actually to form a network. So each neuron here will transmit some inputs. These inputs are weighted by multiplying them with some weights. A bias is added, and then the receiving neuron will add all these inputs coming into a single value, apply the activation function, and then transmit the result to the next neuron, and so on and so forth. So the weight represents information being used by the net to solve a problem. As we shall see, the learning process that takes place in neural network actually simply means adjusting these weights so that the expected output is reached. The weights represent information being used by the net to solve a problem. Alright, so as we shall see, actually the network learns from the examples by making adjustment to these weights until the value it produces output here matches what is expected. We shall see this in detail when we look at how training takes place in neural networks. Now, each neuron has an internal state called its activation or activity level, which is a function of the inputs it has received. As I already explained, the summation here of these products of weights and input values plus the bias are passed through a function. So that function is what we are talking about here. This is the activation function. Typically, a neuron sends its activation as a signal to several other neurons. So as you can see in this network, even though here the output is shown as single output, usually it is transmitted to several neurons. For example, if you take this neuron, it is transmitting its output to all these other neurons. A neuron can send only one signal at a time, although that signal is broadcast to several other neurons. So again, this is obvious from the diagram we are seeing here. Only one signal is sent at a time, but the signal is broadcast to the neighboring neurons so that they each receive the same amount of signal. Now, several key features of the processing elements of artificial neural network are clearly suggested by the properties that we just studied of biological neurons. We saw that artificial neuron has a processing element, okay, and the processing element receives many signals through these input lines that you are seeing, just like the biological neurons also receive signals from neighboring neurons through its dendrites. Okay, the second similarity is that signals may be modified by a weight at the receiving synapse. Okay, each signal received here is multiplied by certain weights, thus modifying its effect. Okay, just like we said, the synapse in biological neuron will regulate the amount of signal that is being received from other neurons. Another similarity is that the processing elements sum up the weighted inputs. Just like in the biological neurons, the different signals that are received through the dendrites are combined together to form a total sum amount. And the neuron transmits a single output. Just like in the biological neuron, it will transmit a single output through its axon once the signal reaches a certain threshold. The output from a particular neuron may go to many other neurons. Again, this is exactly what happens in the biological neurons. So you can see that there are many similarities therefore, which is natural since the artificial neuron is being modeled from the biological neuron. So generally, if we consider the neural network as a whole, say ANNs are generally organized into layers as shown in the figure on the right. So here we have the input layer, and at the end here we have the output layer. In the middle we may have one or more hidden layers. The input layer represents the input features. Okay, they pass the information to the next layer, which is the hidden layer most of the time. But sometimes, as we shall see in the simplest type of network, the information actually may be transmitted directly from input layer to output layer. Okay, so we may have hidden nodes, or what is called hidden layer. It represents intermediate processing that is done before the final output is computed. So the hidden layer will receive input from, let's say, an input layer, apply its activation function, and then pass the output to the next layer. And then finally we have the output nodes, or what is called the output layer. So this represents the class levels. Okay, the actual output that we want. Most cases it is a classification that we are actually trying to achieve. So the different classes will now be obtained through the output layer. For example, in the last example that we learned in the previous lecture, the data from the restaurant was used to classify different inputs into will wait or will not wait. And, those customers that decide that they will wait given the condition that they made the restaurant, and those that decide that they will not wait. So let's take an example to see how this actually works. So as you can see in this diagram, two inputs, x1 and x2, are received. They are going to be multiplied by certain weights. Okay, so x1 times w1 and x2 times w2. The products of inputs and associated weights from different input lines are summed up together, and then a bias is added. Alright, so something like this. So we already have multiplied each of the x1 and x2 by a certain weight. Now add them together. Also add a bias. So this is the next process. Once we have this, the next step now is to apply the activation function. So an activation function is applied to the sum, usually to squash the value obtained from the sum so that it is within a certain range, usually between 0 and 1. Okay, so this is what we are showing here. The function will be applied to the sum and we get a single output y. Okay, and this y, as I said, this function will try to make sure it is within a certain range. So the question is, what is the nature of this activation function that transforms the sum of the input into a value that falls within a certain range? Well, there are many types of activation functions that are used in neural networks to squash the output to a desired range. However, among the most commonly used is the sigmoid function, sigmoid of x. So how do we define sigmoid of x? Sigmoid of x is actually this function, 1 divided by 1 plus e to the power minus x. Now, sigmoid function has a very nice property, as you can see in this graph, which is that no matter the value of x it receives, no matter how big or how small, the results you are going to get is going to lie between 0 and 1 and will never go outside that. So even if you give 100 million, you will simply get a value that is approaching 1, okay, but will never go beyond 1. Similarly here, if you give a negative value of x, you will get a value that is close to 0. So the smaller the value of x, the closer it is to 0. And the bigger the value of x, the closer it is to 1. But the value will never go outside this range. So this is basically what the sigmoid function does, which makes it very useful in neural networks. It has other nice feature, which is that it is differentiable. As we shall see, when training a network, we need to be computing what are called errors. Now, these errors are normally obtained by taking the derivative of the function. Well, the good news is that this sigmoid function is differentiable, and the derivative is also very easy. It is simply sigmoid of x times 1 minus sigmoid of x. So it is very easy to compute the derivative. Yeah, so this is what I'm saying here, that differentiability of this function makes it easy to compute the learning error which is required during the training. So let us take a very small example to demonstrate how this computation at the neuron is done in practice. Okay, so example number 1, or trivial example number 1. Given a sample of 2 features, x1 and x2, and 2 associated weights, w1 and w2, compute the output y of an ANN of single neuron, where w is equal to 0, 1. So w here is given as a vector consisting of 0 for the w1 and 1 for the W2. Similarly, x is given as a vector where x1 is equal to 2 and x2 is equal to 3. We are also given that the bias B is equal to 4. So it's really very easy. You just need to apply your summation formula. Okay, so it's always going to be the inner product of the two vectors, W and X. So W dot X plus bias, which means W1 times X1 plus W2 times X2 plus the bias B. And this is going to be 0 times 2, okay, plus 1 times 3 plus 4, which is equal to 7. So this is your summation, and the next step therefore is to apply the activation function, which in this case is the sigmoid function. So sigmoid of your summation here is simply going to be f of 7, and the f of 7 is 0.999. Alright, let's take another example, trivial example number 2. This time we will take a network that has a hidden layer actually, as you can see here. So using the network on the right, compute the values H1 and H2. Okay, so the values that are transmitted to the hidden layer, which consists of H1 and H2, and also the output O1. Using the sigmoid activation function in both cases, and also given that the two vectors W and X are the same as in the previous example, 0, 1 for the weight and 2, 3 for the X. But the bias this time is 0. Now we're going to assume that the weights are going to be the same, both in computing the H. So the weights are going to be applied to X1 and X2 as given here, but also here in transforming from the H to O, we will use the same weights. So let's proceed. H1 is going to be equal to H2, and it's going to be equal to the products of the X and the W's plus the bias. So it's going to be like before, 0 times 2 plus 1 times 3 plus the bias, which is 0, and this time because there is no bias, you're going to get 3, and sigmoid of 3 is 0.9526. So the same weights, as you can see, are used in computing H1. Similarly, the same weights are going to be used in computing H2, and that's why the two H's are equal. Okay, it may not be the same in practice. You may have different weights depending on which neuron you are going into. Okay, so but this is a trivial example, so we are taking them to be the same. So now that we have computed H1 and H2, we should be able to compute output 1. So output 1 is the same weight that is used. So it's going to be this vector here, 0, 1, times the output of these two nodes, which will be now serving as input to the O neuron here. Alright, so they are basically the values we computed. They are both the same, 0.9526. H1, H2 are the same values. So just multiply that, add the bias, the same bias till 0, and see what you have. So we're going to have 0 times H1. So obviously it means that this term will be eliminated. We are left with just the H2. So H2, if you multiply by the weight 1 we will have just the H2. Okay, so just apply the activation function F and you will have 0.7216 as the result. Okay, so this is just to give you an example of how this computation is done in real life. But now let's start to look at the neural networks in more detail, especially to learn how they actually learn from examples, because that's the main purpose of this lecture. How do we train a network to learn by example? I'm going to start with the simplest of neural networks, which is the perceptron, single layer artificial neural network. So the simplest type of ANN is the single layer ANN, which is also called the perceptron. And this is how it looks. So we have just from input to output directly. There are no hidden layers involved. Alright, of course, as usual, we have the associated weights. So each input here is going to be weighted, and there will be a bias. So sum the different products, then apply the activation function, and you get your output directly. No hidden layers involved. Alright, so perceptrons are generally used to classify data into classes, provided the data can be separated linearly. Okay, or provided the data is linearly separable. As we shall explain in a moment, perceptron is only applicable to data that is linearly separable. Now, because of their nature of classifying data into two components, they are generally called linear binary classifiers. So how does perceptron learn from examples? So learning in ANNs generally involves repeatedly comparing the predicted outputs, which we call Y-pred, against the actual outputs, which we call Y-true. How do we get the actual output? Well, from the examples. Like what we saw in the previous lecture, we had sample data where for each row we have the different combinations of the attributes, and the last attribute tell us the class. Is the customer going to wait or not? So we know the actual output and we know the input. So that's what we are saying here. The class column will normally tell us the true value of expected output. And now our network compute a predicted output based on just the input attributes without including the value of this class column. Okay, so the two values are compared. The error is minimized. And now, how do we minimize the error? It's basically by adjusting the weights that are applied to the input values, because you cannot, of course, change the input values, but you can change the weights and you can change the bias, and you try again. You repeatedly do this until the error between the predicted output and the true output is minimal. Here is the full algorithm for learning using the perceptron artificial neural network. First, we initialize the weights and the bias with random values. Okay, so initially the weights are just random. Okay, then present the next set of input values from the training data to the network and compute the predicted output. We saw how to do this with the trivial examples we have seen. Once we are given the input values, the x, and we have generated the weights, so the weights are initially generated randomly, we can compute the summation, and we can apply the activation function and compute the predicted output. Alright, so once we have the predicted output, the next step is to compute the error. Now, a common way to compute the error is using what is called mean square error, MSE, and it is defined by this formula: 1/n times the summation of y true minus y pred square. The y pred minus the y true minus y pred square is actually what is called the squared error. Alright, but normally you take this across all the input that you have in the training data and take the average. So that's why we are adding all of them here across the input data values and then taking the average. This will give you the mean square error. Of course, initially this mean square error may be big because we started with just random values of the weights. So what you do is you adjust the weights by subtracting this error from the current weights. Okay, so that's the next step. Say adjust the weights using this formula. So each weight is going to be its current value plus some delta Wi, where delta Wi is actually minus learning rate, which is called R, times the value of the MSE. So you're gonna basically subtract this error from the current weight, thus giving you a new value of the weight. And then you repeat the process. So repeat from step 2 until an acceptable error is reached. So you will see that as you repeat this process, the error here will be becoming smaller and smaller, and therefore your predicted output will be moving closer to your expected output. So you're going to repeat this process until when the error reaches a reasonable point, at which point you are confident that the network has learned the relationship between your input and the output, that it will be able to work even if you give it now an input that is not inside your training data. This is essentially how Perceptron learns. So we start with random weights, we compute the output, compute the mean square error, subtract this error from the weights, and repeat the process until the error reaches an acceptable state. Now Perceptron, as I mentioned earlier, has limitation. It is only applicable to data values that can be linearly separated, which are called linearly separable. Alright, so that's what we are saying here, that usefulness of Perceptron is limited because it is applicable only when the data is linearly separable. And these are examples of linearly separable data. So the Boolean OR and NOT functions are all linearly separable Boolean functions. You can see here 0 or 0 is the only one that will give you 0 in the OR function. Any other combination will give you 1. So if you have 0 and 1, 0 or 1 will give you 1. Okay, similarly 1 or 0 will give you 1. 1 or 1 will give you 1. It is only 0 or 0 that will give you 0. So these are the points that you're going to plot And clearly you can draw a straight line to separate the ones and the zeros. And because you can do that, the OR function is said to be linearly separable. If you take the AND, it's the same thing. In the AND, you will only get a 1 if both your two input values are 1. So if x1 is 1 and x2 is 1, then you're going to get 1. 1 and 1 is 1. Any other combination is 0. So 0 and 0 is 0. 0 and 1 is 0. 1 and 0 is also 0. So again, clearly you can draw a single straight line to separate the zeros and the ones. And therefore, this data is again linearly separable. The last example here is the NOT. So the NOT is a negator. If you give it a 0, it will change it to 1. If you give it a 1, it will change it to 0. So you can separate the two values into ones and zeros. But if you take the XOR function, the XOR Boolean function, unfortunately, is not linearly separable. So as we remember, XOR means exclusive OR. So we're going to get a 1 only if one of the two input is 1. Alright, so here 0 XOR 0, of course, will give 0. If you have 1 or 0, you're going to get 1. 0 or 1 will give you 1. But 1 or 1, since we are talking about exclusive OR, is actually going to be 0. The question is there a way to draw a straight line that will split the zeros and ones in this case? Clearly there is no way. If you draw a line like this, it's not going to work. This will not work. No diagonal will work either. So there is no way to draw a single line to separate these output values. And therefore XOR is a typical example of linearly unseparable data. Now this type of problem, you cannot solve it using Perceptron. Perceptron classifier cannot classify data that is like this, whereas it can very easily learn how to separate these two different outputs of zeros and ones. This is another example of linearly separable and linearly unseparable data. So the figure A here, clearly it will be able to separate this data values between greens and blues, because we can draw a single straight line to have the data classified. What about here? Obviously there is no way to have a straight line that can classify this data. So therefore the data in A can be, Perceptron can be applied to the data in A to achieve the classification, but cannot be applied to the data that we have in B. If we have data that is not linearly separable, the only way we can classify it is by using multi-layer network. For example, the XOR, if we are just to introduce one additional layer, which is the hidden layer, we will see that it will be able to separate the two. Because what we have actually, if we introduce another layer, we will be able to draw another line, okay, another plane, okay, or hyperplane as it is called, that will allow us to actually separate the data into two groups. Okay, so now you can see the positives, or the ones, will be as highlighted here in the shaded rectangle, whereas the negatives are the ones outside. Okay, so hidden layer allows you to introduce more boundaries, and you will be able to separate your outputs into two classes. And this naturally therefore takes us to multi-layer ANNs. Okay, so multi-layer networks solve the classification problem for even nonlinear sets by employing hidden layers. Okay, by employing additional hidden layers. The additional hidden layers can be interpreted geometrically as additional hyperplanes, which will enhance the separation capacity of the network. Okay, so this is an example of a multi-layer network as we have been seeing it in the earlier slides. In addition to the input layer and the output layer, now we have a layer in the middle, which is called hidden layer. Now the question is, how does this kind of network learn? In other words, what constitutes an error in the hidden layers? We know that in the output layer, we can compute the error because we know the expected output. So we just subtract the predicted output from the expected output and square it to get the squared error. But in hidden layer, there is no expected output. Okay, we only have the predicted output. So the question is, how do we compute the error in this case? Okay, this was actually a huge problem to initial AI practitioners. And actually that was what slowed down the development of artificial neural network for quite some time at the initial state, until at later time when people discovered an algorithm that allow even multi-layer neural network to learn. And that is the backpropagation algorithm. Okay, so let's briefly look at backpropagation algorithm. I will not go into the detailed mathematics about it because that is beyond this introductory course, but there's a detailed algorithm that is used in this backpropagation. And also the good news is that there are many libraries nowadays in modern programming languages like Python that actually have these algorithms implemented. So you just apply the relevant algorithm and you will be able to train your network. So let's go through. It's a learning in multi-layer ANNs is achieved by propagating the error at the output layer back to the hidden layers. This is basically the main idea. So you cannot do the adjustment until you get the final output, which is obtained at the output layer. Now compute the error at the output layer and then propagate it back proportionally to the nodes in the layer immediately before the output layer. Okay, depending on the weight that was applied, to each node in that layer, in the same order, the error is going to be propagated back proportionally to each node. Okay, this is the idea. So the process is as follows. Say for the output layer, the weight updating is similar to what we do in the perceptrons, because here we know exactly what is the output, and therefore we can compute the squared error, and we can be able to adjust the weight accordingly. However, before you adjust the weight and start the process, you have to compute what will be the weight for the layers before the output layer. Okay, the hidden layers back until you reach back to the input layer. How do you adjust the weight in those cases? So this is where the backpropagation is done. It's for each hidden layer from the output going back until the input. For each hidden layer, and then for each unit, or for each neuron, or for each cell in the layer, determine how much it contributed to the error in the previous run. How much did it contribute to the error? So this is what I meant. When you compute the total error at the output, you have to now ration it to each node in the preceding immediate layer, and each one proportionally according to how it contributed to that error. Okay, so essentially we have to look at the weight that was applied to reach from that particular node to the output layer, and so based on the values of those weights, the errors will be distributed accordingly. Okay, and this is normally done using partial derivatives, and as I said, I will not go into the detailed mathematics involved, but this is the essence. Proportion the error back to each node, depending on how much it contributed to that error. So once you have that, now you're gonna adapt the weights according to this contribution. So for each node, after we computed the error it has contributed, we're gonna adjust its weight accordingly. Okay, and we repeat the process. So now that we have obtained this error at this layer, we now again propagate it back to the preceding layer, and we repeat the process until we reach the input layer, and we will be able to adjust the weights accordingly. Yeah, so this is basically how backpropagation works in summary, without going into the detail of the mathematics involved. Now, in terms of designing a neural network, there are certain issues that we should be clear about. The first is the number of nodes in the input layer. How many nodes should we have in the input layer? Now, this answer is very clear. It simply depends on the number of features or attributes that you have in your input. Okay, so this is very clear. Each feature will be represented by a single node. What about the number of nodes that you're going to need in the output layer? So again, this depends on the number of classes you're going to need. Do you need just 2 classes? For example, in the case of binary classification, we just want yes or no. Or is it a multi-class problem? Like, for example, if you are implementing a network to recognize handwritten digits, for example. Okay, automatic character recognition, but in this case just for the digits. So we know, of course, there are 10 digits, 0 to 9. All right, so in this case you cannot have just 2 nodes in the output layer to give you the zeros and 1, as in the case of binary. Here we need 10 nodes in the output layer, 1 for each digit, and so on. So it basically depends on the classes that you expect to have in the data that you are dealing with. That will determine the number of nodes in the output layer. All right, the next question is, what is the number of nodes in the hidden layer? This is the big question. How many nodes do you have in the hidden layer? For this one, there is no specific rule actually. It all depends on the experimentation. Although many authors suggest that you should not have as many as twice the number of nodes in the preceding layer. So if you have, for example, 4 nodes in the input layer, then the hidden layer immediately after should not have up to 8. Okay, you could have anywhere in between. So you could have 7, 6, 5, and so on. But you shouldn't have as much as twice the number in the preceding layer, and so on. So there are some suggestions like that, but in general there is no specific rule. It really very much depends on experimentation. So you have to try and see in your experiments to see what number of nodes give you the best output, again depending on the problem that you are trying to solve. Okay, the next question is, what should be the initial weights and the initial biases? So again, this is very simple. The initial weights and biases are generated randomly. So just use a random generator to generate the weights initially. Of course, at the beginning, the error you're going to get is going to be very large, because this weight that you assign randomly, they have no relation to the input that you applied, and therefore we cannot expect the result to be similar to the output you are expecting. But as you repeat the process, compute the squared error, adjust the weights, and then try again, eventually the weights will converge to values that will give you output that is very close to your expected output. So these are some of the design issues if you are doing an experiment on neural network. And then let's talk briefly about the characteristics of artificial neural networks. So multi-layer ANNs are universal approximators, but they could suffer actually from what is called overfitting. So this usually happens if you have a network that is too large compared to the problem you are trying to solve. So you have too many layers, too many nodes. You apply your training data. The training data will almost fit one-to-one to your network. Okay, and therefore if you apply now data that is not in the training, okay, you try your test data, you will see that the network doesn't perform well, because the network is almost a fixed network based on the data that you use for the training. All right, so it's not good to have the network to have too many layers and too many nodes. Doing that could lead to overfitting. So the network is like it has fit your training data too much, so that with the training data you are getting almost exact output as similar to the output you are expecting. But if you try the test data, then you will see that the result you get is not as good. All right, so we try to control this again with the experimentation to make sure the network doesn't overfit. Another characteristics of artificial neural network is that the gradient descent, that is the error that you compute, usually using the mean squared error, may converge to a local minimum. So you have to be careful about this as well. Depending on the activation function that you use, the error could actually converge to a local minimum rather than the actual minimum that you need to have for you to minimize the error. Okay, another characteristic is that model building can be very time consuming, as we have seen, there are many issues that are not clear. You have to try them by experiment, and therefore the experimentation can take time. But once you are able to have a good representation of your network based on the data that you have, you see that the testing can be very fast. Of course, another properties is that they can handle redundant attributes because weights are automatically learned. Okay, so similar to what we saw in decision trees, the neural networks can handle redundant attributes very easily. Okay, because the network learns simply by adjusting the weights, so it doesn't. The redundant attributes will not affect the overall output. But the network can be also sensitive to noise in the training data. So if you have outliers, many outliers in your training data, this is likely to affect the performance of your network. So that by the time you start testing, you may see that the output you get is not as good as expected. Okay, so these are things to be careful about. Sometimes you may need to do pre-processing to try and eliminate those data values that are actually outliers, so that your network can learn in a better way. All right, so before we conclude this lecture, I would just like to give a brief overview of deep neural networks. I'm sure you have heard the buzzword of the day in the AI, which is deep learning. So the question is, what is deep learning? Okay, so deep learning is simply the application of deep neural networks in order to solve very complex problems. So what are deep neural networks? Deep neural networks involve a large number of hidden layers. This is basically the difference. So in simple networks, we may have one or two hidden layers, as you can see here. But in deep neural networks, you have many hidden layers. So that's basically the difference. The extra layers provide a huge increase in computational power, which have allowed this deep neural network to reach amazing performance in multiple type of tasks. Okay, they are able to solve very complex problems, and actually they are being used by this big technology companies like Google to solve many big AI problems. They can represent features at multiple levels of abstraction, basically, because each layer is introducing another level of abstraction, and therefore they can represent different features at different level of abstraction. Deep networks have become the technique of choice for problems such as vision, audio, and natural language processing. So this is mostly where you see this type of network being applied. What are the challenges in deep neural networks? Well, they are usually slow to converge. So slow convergence is an issue. Convergence here means the predicted output getting closer and closer to the expected output may be slow. Sensitivity to initial values of model parameters. The larger number of nodes make deep networks susceptible to overfitting. So as we discussed before, if the network is large, it may be susceptible to overfitting, but we will see how these issues are solved in the next point. So what are the solutions to this big challenges as far as deep neural networks is concerned? Well, the first and most important solution is that in situation where deep neural networks are used, usually you have large training data sets. The training data set is really very large. Okay, so if you have very large sets of data, issues like overfitting will not come in actually, because overfitting normally comes when you have the network is too big relative to the training data. Okay, so if it's too big relative to the training data, definitely you will have overfitting. But if you have large training data, then you will see that the network will just be appropriate, and you will be avoiding the problem of overfitting. Okay, so this is one point. Also, of course, nowadays we have computers that are computationally more powerful than we used to have. Computers with GPUs, for example, and therefore the issue of slow convergence is now really taken care of, because these computers can repeat the experiment at incredibly fast speed. So the issue of slow convergence is being solved with these additional powers that we have in modern computers. Also, there are advances in the algorithms that are used. For example, there are now better activation functions. Instead of relying on the sigmoid functions, for example, there are now many other ways to achieve the activation. Better parameter selections are now available, and also more efficient error minimization algorithms are now available. Okay, so all these factors, if you combine them together, you see that this is actually how the issues that we listed here are overcome. And deep neural networks are now really the order of the day, especially in problems that are very complex and that involve large amount of data. I would like to conclude this lecture by giving you this link at the bottom, which discuss different types of neural networks that have been experimented by AI people across the world. In this lecture, we discuss very simple networks, but actually there are many different types of neural networks. So if you click this link, it will explain each of this network. What does it actually mean? How is it normally used? How is it different from the others, and so on. So I suggest if you have time, please go through it so that you will have more information about how neural networks are and what type of neural networks do we have. Right, so with this we come to the end of this lecture. Thank you very much.